Good morning, everyone. Welcome to IEEE Charlotte Section 2025 Technical Seminar Series. So my name is Xiuhu Sun, and I'm the chair of IEEE Charlotte Section PALS IES Joint Chapter. So it's my pleasure to host today's seminar. Today's topic is DC solid circuit breakers, shaping the future of power protection. And our speaker today is Dr. Shuyan Zhao, senior member of IEEE and a research scientist with ABB Corporate Research in Raleigh, North Carolina. Dr. Zhao received his bachelor degree from Wuhan University in 2017, his master's degree from the China University of Mining and Technology in 2020, and his PhD degree from Drexel University in 2024, all in electrical engineering. So his research focuses on high voltage wide bandgap semiconductor, solid state power protection, and wireless power transfer technology. So Dr. has made an important contribution to the field of DC protection and advanced power electronics. And today, he will share with us his insights into how solid-state circuit breakers are reshaping the future of DC power systems. After Dr. talk, we will have a short Q&A section, so please feel free to note down your question as we go. And if you would like to learn more about Dr. Zhao's research, you can visit his Google Scholar or LinkedIn profiles using the QR code shown on the flyer. So now let's welcome Dr. Zhao to begin his presentation. So Dr. Zhao.
Yeah, sure. Can you hear me?
Yeah.
Okay,
So
let me share my screen.
Yeah, you can see your screen now.
Can you see my screen?
Yes, I can see it.
Okay, let me get started. So, hello everyone, welcome to this seminar. So my topic today is going to be this DC solid state circuit breakers and shaping the future of power protection in the DC system. So the contents like agenda today can be divided into like 8 or 7 parts, like if time allows. But if the time like is not allowed to cover all the contents here, please just let me know, okay? And we can like stop and reserve for next time. So I start with introduction and then principles of solid state circuit breakers, and then solid state circuit breaker technology, mainly like power semiconductor technologies for solid state circuit breakers, and circuit topologies for solid state breakers, and voltage clamping circuits for solid state circuit breakers, and also fault sense and chip electronic circuits for sorry, there's a typo here. It's just fault sense and the chip electronics for solid state circuit breakers here, and with references. So let me get started with introduction part first. So we have this technology of solid state circuit breakers now, like mainly by ABB and some other key like startup companies now. So there are a few benefits of this technology, like mainly like 6 points here. So first, of course, the response time, that's the main benefits of solid state like semiconductor devices. It's like several orders of magnitude shorter than electromechanical, like conventional technology, right? Like conventional circuit breakers, they typically have their response time default at like millisecond or hundreds of milliseconds. That's typically very slow for a DC system. And unlike the electromechanical circuit breakers, which relies on contact, like actual like metal contact separation for interruption, so semiconductor devices can like interrupt the electric flow without arcing. That's another like arcless like switching. That's another benefit. And third is like due to the extremely fast interruption capability. So semiconductor-based this type of circuit breaker can like effectively limit the let-through energy and then hence like the arc hazard exposure like in fault event by multiple orders of magnitude, like also compared to traditional technology like electromechanical, right? So, and then because of the absence of moving parts, like, I mean, the contact separation, that's called moving part, the power semiconductor devices can execute a much higher number of operations, like increased the lifetime of circuit breakers. And because semiconductor devices have no moving parts also, there's other benefits that of course, they operate without making any noise, right? Like unlike the metal contacts, it's always like comes with like a big noise. And additional benefits that may be application specific. So basically, like 5 major like benefits here I want to summarize is like response speed, no arcing, let through energy and arc exposure are limited, increased lifetime, and noise-free operation. So there are some, so the major motivation that we propose or develop this technology is like there are, you may also have heard that there are like emerging power system application and they are facing like a few challenges here. So, and that's what like DC solid state circuit breakers want to like merge into or want to like participate in or like help to like solve those challenges in those like emerging power system applications. So like marine power distribution system like DC, also like data centers like DC, right? 800 DC recently published by NVIDIA, and aviation, power distribution, battery protection, photovoltaic system, power converter protection, railway power system, defense power system, electric vehicle charging infrastructure. That's typical like application that the DC solid state circuit breakers can find a position in. So here is like some more specific description of typical application and some challenges here, and also example here. So most of these applications use like low voltage, like up to 1500 volts, and lower range of medium voltage, like 5 to 10 kilovolts DC power distribution. Okay. So yes, so low voltage DC and lower range of medium voltage DC power distribution for superior system level benefits. So there are two like major like benefits here that I want to summarize. Is first is like the higher for this type of DC applications. Why we choose this DC or low voltage DC or medium voltage DC instead of AC? Because higher efficiency of power generation on this example, like electric ships and marine platforms. And second, that is more common, more general, is reduction of power conversion stages and hence increased efficiency in data centers, renewable integrations, and flexible EV charging infrastructure. And here, the right side shows a example of a shipboard DC power system, and there are multiple features here. So using this medium voltage DC, 20 kilovolts, and LVDC, 1 kilovolts for power distribution on ships, and using medium voltage solid state circuit breakers here, and low voltage solid state circuit breakers here for faster fault protection. And another feature for the system architecture is like there are like dual, as you can see, they are like 1 and 2. They are dual like bus transfer architecture for higher reliability. Okay, and so this type of DC distribution systems, like despite clear benefits, are still facing challenges. So requiring higher performance protection devices than electromechanical circuit breakers. That's why the solid-state circuit breakers find the position. So existing like electromechanical protection solutions have limited capability for DC protection due to very high fault current magnitude and rise rate VIDT. And short circuit detection and interruption involves several moving parts like contacts and hence slow response speed, even for best in class like electromechanical parts. They are like still have like relatively slow response speed in a few milliseconds. And due to the absence of natural zero current crossings in DC, mechanical circuit breakers require additional like arc extinguishing mechanism to drive fault current to zero. So then comes to solid-state circuit breakers. It has much faster response speed and extremely fast reaction speed of power electronics devices. That is the reason. And turn off semiconductor devices like here. And current limiting action can happen in microseconds. That's how like the solid circuit breakers like greatly improve the fault interruption speed in DC system. So here is for us the ABB. We have the I think the world first IEC certified solid state circuit breakers products now. So this is our offering of solid state circuit breakers called CS Infinitus. So this is like with the frame size being able to handle up to 2.5 kiloamps and operation up to 1.25 kilovolts DC. So CS Infinitus functions as a circuit breaker or conductor or isolator or an energy meter and offers a wide range of communication options. This all-in-one device delivers like disruptive performance, ensuring like safety and reliability while like reducing space and costs. So there are a few like features like all-in-one solutions, breaker, switch, isolator, and connectivity hub, and it features like 1,000 times faster. So near zero break-in time, like microsecond, right? Compared to fastest traditional protection technology like electromechanical breakers, maximizing service continuity. And this like less like 70% losses for low technology like costs of ownership. So maximize energy efficiency with a new switching technology and that has lowest power losses in solid state protection. And more importantly, it's near zero arc energy exposure. So it's like no energy release during current interruption and enabling like true arc flash mitigation for people and equipment. Also, and of course, it's bidirectional protection. So it's like interruption of short circuit current in both directions and unlimited prospective short circuit. That is a like actually a important like index of any like circuit breaker technology, prospective short circuit, and there's for solid state of our product here. So there's no restriction in the value of maximum prospective short circuit current that can be handled by this breaker. So that is actually a really promising technology, and if you're interested, and you are welcome to visit our website of this product here. So here comes our next section, which is some like review of like general working principles of solid state circuit breakers. So first of all, I want to briefly introduce some like key components of solid state circuit breakers to help you have a like somehow like a brief or brief interception or like realization of the like what it is and how many like parts or components it consists of. So some key components of a generic solid state breaker as shown in this figure here. So first, of course, most important is main power semiconductor devices that works as a main switch here. And the gate driver of this semiconductor device, and also its cooling system. And then the voltage clamping circuit in parallel with the main branch, main topology. And also number 5 is fault sensing part or fault sensing system, which consists of like some electronics, and also and sensing and chip electronics. And the last is the auxiliary power supply, which provides like power to all the active components in this architecture here. So a few points here. The number of power semiconductors depends on voltage and current rating of the application, power semiconductor technology, and the topology of the breaker. So really the number of power semiconductors that we care about, because that involves the cost. That's in fact like cost, the topology that we want to use, and the actual performance of it, right? So a few topology that assume slightly different architecture. For example, we have other technology like Z-source or JFET-based self-powered SSCB. SSCB means solid state circuit breakers actually here, and with few others that I probably cannot cover all here, but this is a more generic like solid state circuit breaker architecture here. Okay. Here comes our solid state switching operation. This is part 1. So the right side here shows a representative waveform of solid state switching operation here. So in the beginning, so during normal operation, so this is normal operation, the power semiconductor device is stay in on state. So the gate driver actually like units. This unit applies appropriate bias voltage or current to the power semiconductor gate terminal to keep it like in a stable and low resistance on state. And the sensing and chip electronics continuously monitor the electronics. My headphone has. Can you hear me now?
Yeah.
Okay. So the sensing and chip electronics continuously just monitors the breaker current here, which like actually means like here, the nominal current here. So whenever there's a fault happens, like then the sense and chip electronics will like detect the fault like here. So when there's a fault happens here, there's a fault event, and then we'll see the system current or the breaker's current like increase like very fast or very high rate of rise of the current here, like a linear rising if it is short circuit fault. So then at some point the sense and the fault sensing like units will detect this fault, and it will send signals to the main switches and other electronic components to get ready to turn off the breaker or turn off the main switch, power semiconductor devices first. It comes to this area which called like fault interruption area. So let's say like when our main switch, this is power semiconductor current in this blue waveform. So whenever the fault is detected and the chip unit like give like turn off command to the driver of power semiconductor device. So power semiconductor device current will drop very quick because typically those semiconductors can provide like turn off the like tube current or switch current in like microsecond or even faster, like nanosecond or tens of nanosecond time range. So the semiconductor current will drop off very fast, and then the original current that flows through the main switch will be force commutated to the voltage clamping circuit branch. Then that comes to this part. So the residual energy, because we see like the system like typically has inductance or impedance that we call. So during that typical or fault interruption, before the fault interruption, there is like some current flows through that line inductance, right, or impedance that stores some energy in the system actually. And when we turn off the semiconductor, this residual energy in the system inductance builds up the voltage on the power semiconductor device, like here. So it will rise up very quickly. So when this voltage reach a certain value here, voltage clamping circuit, that's what it's called, right? Voltage clamping circuit get activated, and the voltage is clamped to a safe level for power semiconductors. And this voltage clamping circuit absorbs all the residual system energy. So the system current is driven to zero. And both power semiconductor and voltage clamping circuit are in high impedance states. And then in the end, so voltage across the circuit breakers settles to the system voltage. Also, the system current is practically zero in the end. That's how solid state circuit breaker cut off a fault in a system. More statistically, a DC system. And then next section is the technologies of solid state circuit breakers. And we will first talk about the power semiconductor technologies for solid state circuit breakers. So different power semiconductors, there are a lot of categories here, right? So different of those technologies are characterized by different properties and determine how a specific device can be used or with others. So some devices conduct current in only one direction, or are able to block voltage only in one direction. That's typically some only a few more statistically only a few of all the semiconductor devices. So this will influence actually topology, of course, right? And what other devices are, what or how, or if any other type of devices are needed together in the topology. Also, how well a topology performs with overcurrent, that's some important point. And passive state of a device, also important because it determines if it's normally on or normally off when no control energy or no control power or gate voltage is applied on the device itself. So here, this table or this diagram actually organize the power semiconductor devices with similar properties into categories. So first, chain bipolar and unipolar devices. So this distinction determines allowed current flow direction, power loss profile, and overcurrent capability and temperature dependency, right? So typically, bipolar devices, they're more like a junction. So when conducting, there's a voltage drop. And unipolar devices, they're more when they're conducting, they're more like a resistance, like small resistance. And the voltage drop is actually a linear, with the the actual device current. So predominant materials also then gets some further categorize those technologies. For example, silicon or silicon carbide, or other wide bandgap materials silicon carbide or gallium nitride. And device structure within each categories, then it's kind of a different structure or different specific semiconductor technologies here. Then determines what exactly this power semiconductor technology is. And so there's some analysis of silicon bipolar devices first. So bipolar device, such as thyristor or ICRs, IGBTs, gates, turn-off thyristors, ETOs, and IGCTs, they can block voltage up to 6.5 to 8.5 kV. That's really high power actually, and a nominal current up to 3 to 6 kiloamps. That's nominal current. So that's actually, those devices are usually typically used or already being used in power systems actually, because they require really high power ratings. So they have very good reliability proven by long-term operation in the field. And they are characterized by very good overcurrent or short circuit capability, especially for thyristors families, SCRs, GTOs, ETOs, and IGCTs actually. This is a typo again. So IGCTs actually. So they are characterized by very good overcurrent and Yes, because those devices are like typically if you are like maybe you already know those devices based on silicon, those are high power, those are like really robust and has been proved by like actual applications now. So next is the medium voltage solid circuit breakers based on like some IGBT devices. IGBT is also like kind of like a robust device with like really high power rating achievable. So for example, in this example, in this work, so IGBT with blocking voltage of 4.5 kV is used in the application of medium voltage bus tied solid circuit breakers. Right? And the architecture is here, like it's for electric chips. And in solid breaker was demonstrating experimental results with a system voltage up to 10 kV DC and 1000 amps with an only like 0.8 microsecond opening time. That's very fast actually. However, IGBT still exhibit relatively higher conduction losses than thyristor-based solutions. That's basically because of some difference of the semiconductor structure. Like so, some other solid state breakers based on IGCT technologies, based on from those works. So for topology one, like here, so this based on asymmetrical IGCT with series diode to form topology one. This is a bidirectional topology, and some anti-series like reverse conducting IGCT to form topology two to still like form a bidirectional solid breaker main topology, and like reverse blocking IGCT, which called like RB IGCT, typically accomplished by integration of like blocking diodes and IGCT on the same die of the semiconductor for substantial like reduction of power losses of this topology. So they actually combine a diode and IGCT in one device. So typically with some like experimental results, there is only 0.9 volts at 1000 volts conduction. So much lower than IGBT and standard IGCT, GTOs, and others technologies. So some implementation example for solid circuit breakers applications here. For example, a solid state breaker based on 2.5 kV reverse blocking IGCT is here. That was validated up to 1 kV voltage DC and turn off current up to 7 kiloamps actually. And this is a two-pole design. So it's for DC applications with nominal 1 kV DC and nominal current 1.5 kiloamps. Was also like demonstrated in some like prior works. And some like solid state circuit breakers based on unipolar wide bandgap semiconductors is also like promising technology now, because wide bandgap semiconductors like silicon carbide show superior material property, enabling higher temperature like this. This is some device from MOSFET actually, and voltages and switching speeds and very low conduction losses per die area. And a substantial amount of research actually have applied these emerging power devices for solid state breaker applications. And say carbide unipolar devices, mainly like JFET or MOSFET, are suitable for SSCB applications because they don't need any supply. Like they are normally on device, or MOSFET they are like also like high voltage, but they still need like control power for BIOS during like on state, because they have a very low RDS on, and also they have relatively higher like blocking voltage capability. Those two are especially suitable for solid state breaker applications among other like unipolar one wide bandgap devices. So like solid state breakers based on SiC JFET devices. So those JFET are normally on device. It has been discussed as a potential good fit for solid state breaker application for two reasons. So JFET has been demonstrated with very low specific on-state resistance, which leads to high current density and high conduction losses per die area. And normally on nature of these devices require no energy to maintain the device in on state of the breaker. That's actually a very energy efficient solution, right? If it's like just passively conduct for a circuit breaker, because like as you know, for a circuit breaker, it's really like being used in turn like for interruption. Like most of its life cycle is on state, right? So however, this nature number 2 also has disadvantages. So if SiC JFET-based solid breaker lose auxiliary power supply, it will exhibit fail on or always on states instead of off. They will lose the capability of turn off, which leads to the loss of protection capability in this case, right? If it's lose the auxiliary power, it will lose the function of circuit breaker. And the implementation example of these JFET-based solid breaker applications are in those works. So for example, one of the work shows a solid breaker for DC system up to 400 volts, nominal voltage 5 amps. That's some like relatively lower, but some like preliminary like concept, I think. A turn-off current up to 200 amps, current interruption time less than 8.8 microsecond. And there are some also special structure called cascaded SiC JFET for high voltage SSAB using single gate drive. So another category is the solid breaker based on SiC MOSFET technology. So MOSFET has been presented as a valuable device for circuit breaker for 2 reasons. Because for SiC MOSFET has like low conduction losses, also high temperature operation, and more importantly, like compared to other wide bandgap devices, market availability is really great for SiC MOSFETs now from a large number of semiconductor manufacturers like Offspeed, like Infineon, like there's a lot of like vendors of this technology now. And implementation example of SiC MOSFET-based breaker applications are a lot actually. So multiple different implementation of this SiC MOSFET-based breakers have been demonstrated for different system voltages from 270 volts up to 850 volts or even higher actually, and turn-off current up to 450 amps, nominal current up to 100 amps with like passive cooling or air cooling or liquid cooling. Like different cooling technology are also like under developing right now. And a medium voltage DC solid breaker implementation with SiC MOSFET has also been demonstrated for system voltage up to 4 kilovolts, nominal current up to 400 amps, turn-off current up to 2000 amps with air cooling, like all passive air cooling. So some other technology like GaN device. So lateral GaN device are like based solid breakers are also like some proof of concept at this moment. So for example, those for DC applications still exhibit too high on-state resistance compared to SiC FETs like MOSFET JFETs. And hopefully the vertical GaN has lowest on-state resistance theoretically, but this technology is not mature or it's not commercial yet for real applications. They're still under developing now. So here is a summary of IV map of major power semiconductor devices in solid breaker literature. So for low voltage applications, for example, this is voltage, right? So for low voltage applications, it's more preferable to use like SiC MOSFET or SiC FET or JFET like here, or silicon SCR or IGBT here. Depends on application current. For medium to high voltage applications, it's like preferable to use silicon IGCT and SCRs also, and I like IGBTs also, like if you want to like series a lot of them. Those devices are like commercial available, but for like SiC ET or GTO, I don't think it's easy to find a very commercial and mature like vendors to provide those devices. So next point is the circuit topology for implementing those technology like circuit breaker topology. So circuit topology supporting solid breaker are like really like dependent on the characteristic of power semiconductor devices, switches, including power loss, cost, size, interruption speed, and other attributes. The first category of topology is based on full controlled power semiconductor devices such as GTO, IGCT, ETO, BJT, IGBT, MOSFET, JFET, and HEMT. This is GAN device. So typically a breaker is required to conduct bidirectional currents and block bipolar voltages as an expected functionality, because in DC system we may more frequently or more often we will see energy storage that really needs like bidirectionality, right? So the anti-parallel placement of reverse blocking switches may provide the lowest loss, since there is only one switch conducting the current like this. So always like if the even like whether the current flow is from left to right or from right to left, there's only one semiconductor conducting at one time. And the parallel of non-reverse blocking switches with series diodes is also feasible. This leads to higher conduction losses, of course, because always there are two devices, there are two junctions, like voltage drop in the past, right? And then supported by a full bridge rectifier structure consisting of 4 diodes, it is possible to use only one fully controllable power semiconductor switch to realize bidirection still. So the switch can be symmetrical, asymmetrical, or a reverse conducting type. That's not actually, that doesn't matter, but you just use the diode bridge to realize, for example, if the current want to flow through left to right, it just flows through this path. If if it's reversed, it just flows through this path. But in any case, it only flows through the same full control switch, but flows through different bridge or bridge of the diode. So the total cost of semiconductor switches is low because only with one full control switch, but it's with the penalty or sacrifice of high conduction losses, as 3 devices are always in the current path, 2 diodes and 1 full control switches, right? And then for lower current range, unipolar FETs have lower conduction losses than bipolar devices because they don't have that p-n junction knee voltage in the forward conduction. But those FET devices are typically reverse conducting, as they have those integral body diodes here for MOSFET, and for IGBTs. Sometimes it's also being co-packaged with this anti-series diode with the IGBT itself. So anti-series topology is suited for them. They are more efficient in synchronous rectification mode because those reverse current is conducting through the channel instead of the body diode. We may want that happens, right? We don't want always the current flow through the body diode. We would like the current always flow through the channel because that's lower losses. And bipolar devices could also use this anti-series topology, for example, for commercial IGBTs. As I said, they are co-packaged with the diode to make the switch reverse conducting, right? But in this case, you have to let the current flow through one diode for the reverse current, right? You have no choice because there is no actual channel. There's actually p-n junction, right? So it cannot flow through the reverse current. Okay, and then the voltage clamping circuit, that's another big part. So those solid breaker in most applications has to withstand this unclamped inductive switching whenever the breakers turn off the current because of the system impedance or inductance and the energy storage inside. So such turn off operation can lead to or easily create severe overvoltage on the power semiconductor devices and causing it to fail permanently. And this can be avoided by a snubber or voltage clamping circuit. We call it VCC. This circuit can be realized by a single or combination of multiple energy absorbing or clamping components. Some driving factors of design of this circuit is we need to figure out the acceptable clamping voltage. We need to figure out the energy absorbing capability. We need to figure out peak fault current in the system, and also the acceptable leakage current at nominal voltage. Sorry. Okay. I'm not sure pointer. Laser here. Okay. So traditional snubber design methods for converters is actually like here we'll make the waveform like this. So for converters, it cannot be directly applied to solid breaker like snubber or voltage clamping circuit design because they are like focused on loss minimization, quick voltage suppression. However, in solid breakers, the waveform is like this. The design of this snubber circuit focus is on the over voltage suppression with much higher or much larger energy absorption capability and a high fault current withstanding capability. As solid state breakers switches very rarely, so energy improvement through this non-dissipative snubber is really not that important or ineffective. So non-dissipative snubber circuit with nonlinear components, merely like capacitor or RC or RCD. Those are like very common power electronics knowledge, right? So limitation applying to solid state breaker application is like due to the LC resonance nature, the performance of voltage clamping is greatly impacted by system parameters like for current level, system inductance, and snubber capacitance. And they are dependent with each other. It's LC resonance, right? So for severe faults with high current and high system inductance, required snubber will be cost and volume prohibitive because that will need a very large capacitance. And a more common clamping solution is by using those metal oxide varistor. We call it MOV. And the fundamental operation principle of MOV is the change of resistance as a function of applied voltage. So during the solid breaker turn-off process, like here, the voltage and current, once the clamping voltage is reached, like here, the voltage across the MOV remains fairly constant, and with a progressive decrease in the voltage as energy or current as energy stored in the system inductance is dissipated in the MOV. And compared to snubber circuits like in the blue here, the blue waveform here, the voltage clamping circuit based on MOV has benefit that clamping voltage performance is fairly decoupled with system parameters now, current or inductance, which ensure a more general solution, which means one solution can fit for a wider like system parameters. And TVS, like TVS diodes, those components have similar performance, but cost is much higher. Also, its performance, like clamping over voltage, is also actually lower than the MOV solutions. So linear like solutions like C, RC, RCD, and nonlinear solutions like MOV or TVS has their pros and cons. And typically, we want a combination of linear and or nonlinear solutions, like MOV with RC or RCD, have more advantages, but of course with higher costs. So clamping circuit of needs to be, the clamping voltage of this type of circuit needs to be carefully designed and selected because there are some trade-off. So on the one hand, selecting higher clamping voltage of those components like MOV brings system current to zero faster, but put more voltage stress on power semiconductor devices, need more switches in series, and it's costly, right? On the other hand, selecting lower clamping voltage puts less voltage stress on like semiconductor, less costly, but it takes more time to bring the system current to zero and then the voltage clamping circuits need to dissipate more energy. And then selecting lower clamping voltage also increase the standby leakage current of voltage clamping components at system nominal voltage, because in the end, it needs to be settled at the nominal voltage, and that's called like standby mode. And we don't want too much standby leakage current, because if it's too much, it's not an off state anymore, right? So at reasonable voltage clamping circuit, clamping voltage or voltage ratio, which is defined by peak over voltage divided by the system nominal voltage, is typically from 1.5 to 2.5. So Xiuhu, I'm not sure if there's enough time, so only 10 minutes left. So how do you think?
Yeah.
Should I cover all the rest or just jump into the Q&A?
Yeah, how many slides do you still have?
Let me see. Oh, just a few.
Okay, just finished.
Okay. So the next is the full sense and chip electronics circuit. So primary function of a breaker, of course, is to stop the current flow during overload or fault events. So this is usually done by sensing fault current in a direct or indirect method or indirect way. For current sensing, there are like different types of for circuit breaker, solid circuit breaker applications. So direct sensing of current, use a dedicated current sensor to continuously measure the current, like Hall effect current sensor, giant magnetoresistive current sensor, or like current sense resistor or shunt resistor current sensor. So the second is indirect sensing of this current. So using system parameters that are dependent on current and the rate of change of current or DIDT for measurement. For example, voltage across the power semiconductor devices, main device, or we add a series connected auxiliary switch, or voltage across an inductor, and then we get the DIDT, and we can kind of use some like analog devices to integrate it to get the actual current. And gate current of power semiconductor devices like SiC JFET reported. Its gate current can be some indicator of the device current or system current. And light emitted by some like SiC JFET die has been reported. The light intensity is like somehow relevant to the current that it conducts. For tripping mechanism, commonly used methods are push-pull key driver, that's direct drive, or turn off, or self-trigger turn off with DSAT. This is typical, like a very common technology for IGBTs, and also now used for SiC MOSFET also. For SCRs, we have some like force commutation circuit to help it turn off because it's semi-controlled device, and gate current injection for IGCTs, GTOs, and other like other technologies of thyristor families. So the tripping characteristic are used as a timing reference during fault protection. So depending on the magnitude of fault current here, the trip time can vary as defined by the I square T requirements for applications. So when current increase slightly, only slightly, for example here, on the magnitude like above the nominal value, the system can handle the excessive heating for longer duration of time, minutes to hours like here. But when the current is like many times larger than its nominal value, like here, it can cause larger heating in very short duration, like millisecond to second, like here. So to achieve this variable tripping time as function of fault current, which we see here as a trip curve, a precise method is have dedicated current sensors and store fault current and time information in a digital processing unit, DSP, microcontroller, or FPGA. And those intelligent units can have a lookup table of trip curve or have mass models to keep track of the actual fault energy that it sends. And this unit can then make a trip decision when appropriate amount of I squared T has occurred. So it allows like tuning of, because those are all like intelligent, it also allows tuning of trip curve depending on like different application requirements, right? For example, for one specific, like one product, one circuit breaker, it may can be compatible with different or multiple chip curves that you can switch over. Yes, that's all. That's basically a review of what is the status of this technology now. And lastly, those are references that's used for this presentation. Yes, thank you. Any questions I would like to answer, please?
Yeah, thank you, Dr. Zhao. So, any question from the audience? You can unmute yourself if you have any questions.
I will. This is a great presentation, Dr. Zhao. It was very informative and very detailed. I loved it, the content. One question I have is, how do you define the mean, or how do you derive the mean time to failure for a solid state circuit breaker?
Mean time
yeah.
to failure, you mean from the reliability point of view?
Reliability point of view, yes.
Yes, typically that's something, because for semiconductor, based our report here or our past experience from those literatures. So typically the semiconductor is totally fine, because for a circuit breaker application, it just always turn on, right? Just stay in on state. So the reliability of our semiconductor is there is no big issue with it for in terms of reliability or lifetime issue. But for the voltage clamping circuit, there are some works that did some research in this. For example, for those MOVs, its lifetime or life cycles actually really dependent on each fault event, how much the fault energy that it will conduct in each fault event, and also what is the line inductance or system inductance that this fault comes with. So it's typically each time how much the fault energy is, and then if each time of this fault energy is higher, then it will have less life cycles for those components, or for the less lifetime for the voltage clamping circuit. That is really some factor that can limit the total lifetime of solid circuit breaker. For example, if each cycle can have a really huge, for example, for current, if it's up to a few kiloamps, and if it comes with a system inductance up to millihenry, maybe it will fail only after tens of short circuit interruption option. But if we properly design the voltage clamping circuit, for example, parallel more of those energy absorbing components, and make sure they are evenly distributed of the current in each event, so it will be extended. So for example, if each MOV only handle each event only handle a few hundred amps at a few micro henry line inductance or impedance, this can work properly for millions of operations, or at least tens of thousands of operations with no reliability issue. Does that answer the question?
Yes, thank you so much. Yeah.
So I have another question, is about lifetime data for the circuit breaker. So compare with the mechanical one. So how about the lifetime? For example, how many time or how long can semiconductor be used in the circuit breakers?
So that's another time about the lifetime, right?
Yeah.
So we know, so for this type of solid circuit breakers, if we properly design the semiconductor and also the voltage clamping circuits, it can work properly with almost forever, right? Millions of operation, millions of fault events, or a few at least a few thousand or tens of thousand times of fault events. For mechanicals, based on my understanding now, the existing standard that regulates lifetime ask it should be capable of ultimate if it's need to operate ultimate short circuit fault, it's at least a few times, and then it need to be replaced or maintained for mechanical breakers, I mean. And for nominal like interruption operation, it requires that to operate properly with like thousands of operations. That's also relatively limited compared to solid state, right? For solid state, we're pretty like flexible to design for lifetime requirements, right?
So you mentioned about the one of the advantage of a solid circuit breaker is no noise.
Yes.
So for example, if some fault happen, if no noise, how the breaker notice the people there's a fault?
That's a good that's a good question. So usually we don't use noise as to indicate that there is a fault in system, right? Because that will be very surprising or really like risky, right? We cannot rely on that. Typically, for a product of circuit breaker like mechanical breaker as we have right now, so they typically has like an indicator, like there's some like LED on the products, right? When it has been tripped, it will just show it. Now the status becomes off, right?
Okay.
For the solid state, it will be the same, right? For the product, there will be some indicator in the front, in the panel of the breaker product itself.
Okay, nice. So any questions from the audience? So Pancake, one question, so what will be the URL for those save the video?
If they're registered, we can send them to the registered email address.
Okay.
Or if they've shared their email address over here, we can share it to them.
Okay, later I'll share the URL on my LinkedIn.
Okay.
If you,
Yeah, we can do that as well. Yeah.
Through email and LinkedIn.
Yeah. I think somebody has a question from the audience.
Yeah, so I will answer the question. So
Yeah, question from the audience. Oftentimes in circuits we have fuses. How much of a premium do we pay for a circuit breaker of similar capacity as the fuse? Like for example, if it's
So that's a good question. So for fuse, typically it's much cheaper than circuit breaker from my understanding. But for example, those solid circuit breaker, one of the major limits that prevent is being massively deployed now is the cost is relatively high, right? For example,
Right.
for our products now, for ABB's solid circuit breaker products at this moment, it's only it's just been designed for really high power application. Share that page. So its application is targeting at some, where it is. Yes, targeting some like really high power distribution applications, like up to 2.5 kiloamps applications. For fuse, from my understanding, typically they are relatively lower power, and more importantly, they are like one-time use. Like when it's like
Right.
melts, you have to replace it, right?
Exactly.
So,
Yes.
but those solid, especially those solid breakers, we can just remotely send in a signal, and it will just reconnect or reclose.
Right.
Yeah,
Remotely controlled.
yes, but yes, another point is yes, your question, to answer your question. So fuse is much cheaper, and circuit breaker or more specifically those solid breakers are much more expensive.
Yes.
And but there are pros and cons. There are compromise, right? So
yeah,
for some applications, if we need like more intelligent protection, we need solid breakers, circuit breakers, like for a more comprehensive protection or more intelligent protection, like faster, for example, for DC. For fuse, it might also be as slow as like millisecond response speed.
right.
And for DC, maybe that's already is not safe anymore, right? For
Yeah, and
but for
especially-
DC, if we have these solid state breakers, it
And remote
typically can.
and the remote resettability is very important in many cases. Okay,
Yes.
thank you. Yeah.
Mhm.
So any more questions? So we already ran over time, so let me just share the last this page. So if you have a further question, you can contact Dr. Zhao through his email, shuyan.zhao@us.abb.com, and also you can connect him, link him on LinkedIn or search his Google Scholar for his other research and in-depth research if you are interested in. So I think that's all for today. Thank you for coming. Thank you very much, Dr. Zhao, for the excellent, insightful presentation.
Thank you.
We also thank everyone for joining today's IEEE Charlotte section technical seminar. So we look forward to see you again at our next seminar. Have a great day, everyone, and thank you for support IEEE Charlotte section. Thank you.